So next, fifth unit, recursive languages and recursive enumerable languages. Okay, so according to Chomsky hierarchy, you know the hierarchy. Okay, so regular grammars are generated, regular grammar generate regular languages and are accepted by the finite state machine or finite automata, right? Then next, context free grammar, which will generate context free languages, and the corresponding machine is push down automata, right? Then next, context sensitive grammar, which generate context sensitive languages, and the machine is linear bounded automata. Then unrestricted grammar, which will generate recursively enumerable languages, and the machine is Turing machine. So this is a type 0 grammar. This is type 0 grammar. This is type 1 grammar. This is type 2 grammar. This is type 3 grammar. This is a Chomsky hierarchy. Okay. So what is recursively enumerable languages? Recursively enumerable languages are the languages generated by unrestricted grammar. That is type 0 grammar. So in this topic, you want to study about what is a recursive language and what is a recursively enumerable language. Okay. Recursive languages, in short REC, are known as Turing decidable language. Okay. Recursive languages are Turing decidable language. Recursive languages are Turing decidable languages. Then what is recursively enumerable language? They are Turing recognizable language. Okay, recursive languages are Turing decidable language. Deciding means the Turing machine definitely halt for some input. Okay, Turing machine will halt and accept the input or halt and reject the input. Definitely Turing machine will halt for some input. In this Turing recognizable language, the Turing machine sometimes will halt or will not halt. So may or may not halt. That is recursively enumerable language. Recursive languages are Turing decidable language. We can decide, okay, whether the Turing machine will halt or not. Okay, definitely there is a Turing machine which will halt for some input. Okay, either it will halt and accept or it will halt and reject on a particular input. When it will accept the string, if the string belongs to the language, suppose I am writing a language L equal to a power and b power and such that n greater than or equal to 1. Okay, so the language consists of the string AB, AA, BB and so on. Okay, if I am checking whether the language AB belongs to this language, it is not belonging to this language. Why? The language is n number of A's followed by n number of B's. Here you can see A, then a B, again A, then a B. Okay, so this pattern is not belonging to this particular language. Okay, so definitely this is not belonging to this particular language. Okay, so if we are giving this input, definitely the Turing machine will halt and reject that particular input string. Okay, if I am checking AAA, B, anywhere this belongs to this particular language, that is AQ, BQ, that is A power and B power n, equal number of A's followed by equal number of B's. Definitely this belongs to the language. So what the Turing machine do? The Turing machine will halt and accept this particular input string. Okay, so anyway this is a decidable language. So recursive languages are Turing decidable languages. A language is said to be recursive. Then there exists a Turing machine which will accept if the string belongs to the language or reject it is not belonging to the language. So definitely the Turing machine will halt for every input and give the answer whether it is accepted or rejected. Okay. Then some properties of recursive languages. There are some properties. So you already saw some properties of context free language, regular languages, etc. So the recursive languages having the properties union. If we are taking two languages L1 and L2, then we are taking the union of L1 and L2, that is also a recursive language. If L1 is a recursive language, L2 is a recursive language, then the union of these two languages is also a recursive language, because definitely if Turing machine will halt for L1 and Turing machine will halt for L2, definitely it will halt for L1 union L2. Okay, then concatenation also. If L1 and L2 are two recursive languages, then if we are performing the concatenation of these two languages, then that is also a recursive language. Next is clean closure. If L1 is a recursive language, then clean closure L1 star. What is star? A star means epsilon, single A, double A, triple A, like that, right? So 0 or more number of A. If we are taking A star, what is A star? A star means epsilon, that is star, that is 0 means epsilon. Then there will be 1A, 2A, 3A, so that is star. Okay, so L1 star means the language. If L1 is a language, if L1 is A, okay, A star, then L1 equal to a language contains a string A, and if I am taking L1 star is A star, then I will get epsilon A, double A, and so on. Okay, so if L1 is a recursive language, definitely L1 star is also a recursive language. Then the intersection of two recursive languages is also a recursive language. Complement of a recursive language is also a recursive language. When you studied about context-free language, the properties, you saw that two context-free languages L1 and L2, if we are performing union operation, then L1 union L2 is also a context-free language, right? Then concatenation, okay, L1 dot L2 is also a context-free language. Clean closure, L1 star is also, if L1 is a context-free language, L1 star is also a context-free language. These are closed, okay. Then intersection and complementation, these two are, that is intersection and complementation, are not closed under context-free languages. These things you studied, right? So in case of recursive languages, union, concatenation, clean closure, intersection and complementation all are closed. Okay, but if I am taking recursively enumerable language, recursively enumerable languages are closed under union, concatenation, clean star closure and intersection, but it is not closed under complementation. Okay, so this is about properties of recursive languages.